Okay, so this is going to be a video just regarding the kinds of differential equations that you can get for leaving Cert Applied Maths. And it is going to be quite a bit of a video because there are 7 of them. One of them is kind of in 2 parts. The main ones I'm going to be dealing with that come up a lot are trig inverses, integration by parts, two-step integration by parts, a substitution, what I like to call the perfect derivative, then a combination of both perfect derivatives and some integration by parts, substitution even, and some second order separable, which are on the course but haven't come up in quite some time. So the first one is utilizing the trig inverses. So obviously we're going to have to do separation of variables here. So what we'll end up doing is I'm going to separate this into blue. So we'll have 2 divided by y squared plus 9 dy equals 3x squared dx, and then we're going to integrate both sides. This is a step that everyone should be able to do if you're leaving certain home, otherwise it'll be a bit concerned. But you can go ahead and try this problem yourself and see if you can get the same answer. We're told that x is 0 when y is pi, and we're told to find y when x is 1. So a common enough one to know is that the integral of 1 divided by x squared plus a squared dx is equal to 1 divided by a times the arctan of x divided by a. So here what we're going to have is we're going to have 2 factoring in as a constant, and then between pi and y, this will just be 1 divided by 3 arctan of y divided by 3 equals, this just integrates to x cubed from 0 and 1. So what we'll have is we'll have 2/3 tan inverse y thirds minus 2/3 tan inverse of pi over 3 equals, that's going to be 1. So we can get an exact solution if we skip a lot here. So we get 1 plus 2/3 tan inverse of pi over 3 coming over. Then we're going to times that by 3/2. So we're going to times the whole thing by 3/2. Then we take the tan of it and times by 3. So it's actually quite a lot. Probably do it in more steps actually. So I think I deliberately made tan inverse of pi over 3 nice, but I can't remember if I can. Okay, well, it doesn't matter. So that's going to end up being about 1.8. So we have 2/3 tan inverse of y thirds equals 1.8. Times that by 3 divided by 2. So I got 1.8 times 3 divided by 2 is 2.7. So tan inverse of y over 3 is 2.7. Take the tan of it and times by 3, so we get 3. Excuse me, we get y equals tan that, so we get 3 tan of 2.7, of course taking our answer in radians. We get about minus 1.4 as our answer there. So the next one is some integration by parts. Now this one is very formulaic, although some people like to use what's known as the DI method. It's not listed as a method, so I wouldn't entirely risk it, but also people who use the DI method are probably just slots who don't enjoy the bit of elbow grease. So the main thing that I have with integration by parts is that you have to set up a little table like this. You set one where you have first function differentiate it, second function integrate it, and the way you detect which one is the derivative and which one is the integral is you use the inlate rule. So whatever one comes first is the one we differentiate. So because the algebra comes first, our u is going to be 2t, which means our derivative is 2. Cosine 3t is going to be the thing we're going to integrate. So we get cosine 3t. If we integrate that, cos integrates to sine. The 3 comes out, so we get 1/3 sine of 3t. Now the formula for this, well, we could actually integrate both sides first. So we'll get dv equals, the integral dv is the integral of 2t cos 3t dt. Now, of course, we could have actually stuck the 2 outside, but it doesn't entirely matter. Where v is 0 at t equals a half, we need to find v at t equals 3 halves. So this just integrates to v. Now this one between 1 half and 3 halves. The way it's going to work is it's going to be u times v. So it's going to be the two sort of normal functions, I guess. So we'll have 2t over 3 sine of 3t. Take away the integral of v times du, which will be 2/3 sine of 3t dt. So what we're going to do here. So the 2t over 3 sine 3t, that's fine. I might have to actually go over a bit. So v equals the integral. Again, we're just going to keep this. That's going to be 2t over 3 sine 3t. Minus, then the integral of this, the 3 comes out, and so we get a 2/9. Sine goes to minus cos, so I'm going to take the plus out, so we get a plus 2/9 cos 3t. So after we sub that in, if we sub in t equals 3 over 2, so we get 2 answer over 3 times sine of 3 answer, plus 2 over 9 cosine of 3 answer. So the first one we get when we sub in 3 halves is minus 1.02. And then we'll take away whatever the one for 1 half is. So 2 answer over 3 sine of 3 answer. Plus 2 over 9 cosine of 3 answer. We get minus 0.35. And so when you work that out, you get v is minus 1.37. So that's integration by parts once, but what happens if you have to do it twice? Well, here's an example of having to do it twice. So we're going to start off the same. We're going to do u dash, v dash. And because I know it's going to be a two-stepper, I'm going to actually do another table here. So in compliance with the in late rule, I'll just write it. This is again dy by dx is e to the 2x cos 3x. I'll just chuck the integral here. So dy is that dx and then integrate. But number 0, we have to find that x equals 1. Perfect. So for the first iteration, we're going to have, again, following the in late rule, we hit trigonometry first. So we're going to have to differentiate the cos 3x, which becomes minus 3 sine of 3x. Then that's, I think we're doing to e to the 2x, which is 1 half e to the 2x. We're going to have a lot more room. So we're going to have, well, it's just going to be y minus 0. So y equals, now u times v, so that's going to be 1 half e to the 2x cos 3x minus the integral of v times du. Now, did put this the wrong way around, so it should be v dash. Oops. So it's going to have u times v, so that's still the same. However, take with the integral of v times du, which is going to be, again, chucking that out, we'll get 3 halves sine 3x e to the 2x dx. And that's going to be the new thing we're going to have to integrate. So we can, again, chuck the 3 halves out because it's just a multiplicative constant. And we can just integrate sine 3x e to the 2x. So again, trigonometry comes first, so sine of 3x, which goes to 3 cos 3x. V dash, again, is our e to the 2x, which becomes 1 half e to the 2x. So we get is y equals 1 half e to the 2x cosine 3x plus 3 halves times The integral is, again, is u times v, so that's going to be 1 half sine 3x e to the 2x. Take away the integral of 1 half e to the 2x sine 3x dx. V times d, that should be cos. Oops. See, I am human. Should be v times du, so that's going to be 1 half. It's going to be minus 3 halves e to the 2x cosine 3x dx. Now, if we have a look, we have e to the 2x cos 3x. So the way we can actually do this is, because we have an e to the 2x, we can actually let y equal the integral of e to the 2x cosine 3x. So what we're going to have is the integral of e to the 2x cosine 3x equals 1 half e to the 2x cosine 3x plus, that's going to be 3/4. 3/4 sine 3x e to the 2x. Again, that's going to come out as minus 3/4 e to the 2x cos 3x dx. Now, if we add this, we get actually 7/4 amounts of the integral of e to the 2x cosine 3x is equal to that. So if we times everything by 4/7, so we get 4/7 of 1 half e to the 2x cosine 3x plus 3/4 sine 3x e to the 2x as our integral. So now what you could do is you could go back, and we know that y is just going to be this entire expression evaluated between 0 and 1 to find a value for y. I'm going to leave that as just an exercise for you to do. It is just some basic substitution. I'm just going to go through the techniques from now. I definitely made a mistake there because it doesn't look like the right answer, but we'll persevere. So number 4 is a trick known as integration by substitution. So again, I'm just going to multiply everything over. So we'll get v plus 2 to the power 4 dv equals ds, and then again we'll integrate. So v is 0 at s is 0, and we have to find v at s equals 3. So the trick here is we actually have to go, in the words of Black Pen, Red Pen, from the v universe, or v world, into a new variable world that I'm going to call u, which is why this is actually sometimes called u substitution. So the substitution I'm going to make is to try get rid of this complicated expression in the middle. So what I'm going to do is I'm going to let u equal to v plus 2. Now, we're going to be integrating u with respect to v, which we can't do. So I'm going to have to get a replacement for dv. So if we take du by dv of this, we get, that's just going to be 1. So du equals to dv. What we'll get therefore is u to the power 4 times, this case, du, which again I'll probably just mark in math green, equals, well, the integral between s and 3, that's going to be 3. So a lot of people like to do what is known as changing the limits. I don't particularly. I like to just solve the integral for u and then chuck it back in the same step. From 0 and v, that becomes u to the 5/5, but this becomes v plus 2 to the 5 all over 5, between 0 and v equals to 3. Sorry about the noise in the background. So what's going to happen is when it's 0, that's going to equal 0. And so we'll just have v plus 2 to the power of 5 equals 15. So v is just 5th root of 15 minus 2. Okay, now the next one looks a bit scary, but it actually shouldn't be, because this is the trick known as the perfect derivative. Now, I split it into actually two parts. I have this one here, And then I have a slightly different example here. So, first one I'm going to do is just multiply across by dx again. So we're going to have integral again. So the integral this time of 3x squared plus 10x plus 5 divided by x cubed plus 5x squared plus 5x plus 9 dx. And then we're going to integrate both sides. So y equals 0 and x equals 1, and we have to find a y at x equals 6. Now the thing to note, and the thing somewhat with this, is that if you note the bottom fraction, if you were to differentiate this, you get a 3x squared plus 10x plus 5. So if you note that the bottom is a derivative of the top, or at least a multiple derivative of the top, then you can just straight up say that y equals the natural log of the bottom. Between 1 and 6. So I wonder if I can do this by hand. So 6 cubed is 216. 36, that's going to be 180 plus 30 plus 9. And then when we chuck a 1 in, we're going to get 1 plus 5 plus 5 plus 9. And so you get y is just the natural log of 396, 425 divided by 20. So that should simplify, because they're about a multiple of 5. Okay, I'm gonna have to give up here. So 425 divided by 20 is the natural log of 85 divided by 4. Okay, so the next one I might have scuppered at 20-ish. You don't actually need these in here because that makes the integral too difficult for an insert. So I might just, so as x, as let's say 3x to the 5 plus 10. Just because with all the other stuff in this trick won't work. So before we saw that this here, the bottom would differentiate perfectly to the top. But what happens if it doesn't do that? So here's the trick. Again, I'm just going to do the normal thing of dy equals x to the 4, 3x to the 5 plus 10 dx, and then integrate. Given x is 1 when y is 1, find y at x equals 10. So there's going to be a y minus 1 cropping out here. Now, if you differentiate this, you get the 5 coming down, you get 15x to the 4 if you differentiate this. Now, that's 15 times too much for a perfect derivative. So if we overshoot bottom, then we're going to have to divide by that scaling factor. So this is equal to 1/15 of the natural log of the bottom. So this can be 3x to the 5. It's 10. Value between 1 and 10. So we're going to have y minus 1 is 1/15 times the natural log of something absolutely ginormous. It's going to be definitely over 13. So 3 times 10 to the 5 is going to be 300,100. Which I don't think divides into 13. No, it definitely doesn't. And then we're just going to have to add 1. So y is 1 plus 1/15 natural log of 300,000. 300,010. Oops. 300,010 divided by 13. Again, I don't think really should be a multiple of 13. Yeah, it's not, but that's the answer. 1 plus 15th log, 300,010 over 13. Now, this question here, I actually made a video of this exact question before, but the video is so old and outdated, like, I absolutely hate it. It's still up if you want to see it. See old me, but I'm just going to do it here because it is what I like to call a combination question. So that is integral number 6. So again, I'm going to multiply across. So dy is 6 log x plus 5 divided by x times 3 log squared of x plus 5 log x plus 4 dx. And then again, we're going to be integrating these. Now y is 1 when x is 2, and let's find y at x is 7. So the trick here is, I actually have to see first that natural log squared of x, this notation is the same as natural log of x squared. There is actually also another two-step integration by parts that uses this. Um, yeah, the integral, if you want to try, is natural log of x divided by x dx, and you get 1/2 log squared of x plus c, as far as I remember. It's something in the form of that, but you can go ahead and try it. So the trick here is we want to notice again that this bottom here is a perfect derivative. However, we can't really deal with log x's and x within the same integral just yet. The trick that I'm going to do is I'm going to let u equal to the natural log of x. So that means that du by dx is going to be 1 divided by x. So to get a dx on its own, we get dx equals x times du. And you can see where this is going to come in, because then we get y minus 1 equals, again, the integral between 2 and 7. This time we're going to be transporting to the u world. 6u 5 divided by x times 3u squared plus 5u is 4. And then times by a replacement for dx, which is x times du. And you can have a look, that x cancels with that x. And again, we just get some more perfect derivative stuff. I'm going to continue over here because I have no room. Or actually, if you found that one fine, you can go ahead and try the second derivative one, or try and move down from one row. Okay, so we get y minus 1 equals, again, now between 2 and 7, it's just the natural log of 3 log squared of x plus 5 log x plus 4. So we have logs in logs. Isn't that fun? Now, I'm going to be just doing some approximate answers here. So for this, we have log of 3 log 7 squared plus 5 log 7 plus 4. And you get about 3.2. Minus, now I'm just going to replace all these with 2's instead of 7's. And we get 2.2. Yeah, that's only an approximate answer, because that turns out to be 1, so y is roughly 2. Obviously, you could go to a lot more decimal places and see that it isn't, but with the way I'm running it, it's 2. Okay, now the final one is a second order differential equation. Now, these are what is known as separable differential equations, and actually, funnily enough, require a u substitution. So the way we're going to do this is we're going to let u equal to dy by dt. So therefore, du by dt equals d2y by dt squared. So we're going to get that du by dt equals to 10 times u. So we're going to get du divided by 10u equals dt. Then integrate. Now we're told y is 0, t is 0. Now we're going to get natural log of 1 equals, natural log is 0, so I might have to change these all to be 1. So it's going to be 1/10 natural log of u equals to t, and then we're going to be evaluating these. We want general expressions, so y is 1, a 2 is 1. So dy by dt, we're going to get du by dt. So dy by dt, that's going to be 1 here. And this is going to go between u, because we're going to stick it in later. and then t is between just 1 and t. So it's going to be 1/10 natural log of u minus 1/10 natural log of 1. That's going to be 0, so we can discount that. Equals t minus 1. So it's going to be 1/10 natural log of u, which was dy by dt, which is, oh dear. So yeah, we'll get natural log of dy by dt equals 10t minus 10. So we're going to have to e both sides, and we get dy by dt equals e to the power of 10t minus 10. So again, we just integrate this fine enough. Again, everything's just going to be 1 and 1, so y and t. We're not going to get an exact numerical answer out of here. So what we can actually do to this is we can note that e to the power of 10t minus 10 is the same as e to the power of 10t over e to the power of 10. So we can actually pluck a 1 divided by e to the power of 10 out, and we get the integral between 1 and t of e to the 10t dt. So we get y minus 1 equals 1 divided by e to the 10, and then between 1 and t of this comes down as 1/10 e to the 10t in there. So y minus 1 is 1 over e to the 10 times, that's going to be 1/10 e to the 10t minus 1 over 10 e to the 10. So we're going to get some cancellation in here, so I'm going to be very careful what I do. So we get e to the 10t divided by 10 e to the 10 minus e to the 10 divided by 10 e to the 10. So those are going to cancel. So therefore y equals 1 plus e to the 10t divided by 10 e to the 10. Now, I haven't done second order separables in a while, so I might have screwed things up a little bit. If I did, please let me know, because I definitely did. And I'm going to expect all these comments, and I have to append a lot of mistakes. But hopefully, at least the tips for different differential equations helps a bit.